For number 1, we've got a 3 kilogram object traveling east at 6 meters per second and a 4 kilogram traveling west. So if it's going this opposite direction, which is like left or west, we have to put a negative sign there. And that's the before. After the collision, the 3 kilogram is now traveling again west at 10, so it should be a negative 10. And the 4 kilogram, we don't know, so that is going to be our unknown. But first it asks, what is the momentum of the 3 kilogram before? So momentum is just mass times velocity. So mass of 3, velocity of 6 gives me a momentum of 18. Momentum of the 4 kilogram, again, mass times velocity. Keep the negative in there because momentum does have direction. That gives me a momentum of negative 32. Total momentum is just the two of them together. So 18 plus negative 32 gives me P total is negative 14. And that just means that my total momentum is in the left direction. E is asking to actually find that missing velocity of the 4 kilogram after the collision. So we're going to plug into our collision equation. We've already actually done the left side, the 3 times 6 plus 4 times negative 8. And we already found that that is 18 and negative 32, so that gives me negative 14. We have not done the after side, which would be 3 times negative 10 plus 4b. So on the right, that gives me negative 30 plus 4v. Now you cannot combine these because they are not like terms, so I'm going to bring this down. Now trying to get v by itself, we want to move the negative 30 over. Opposite of minus 30 is to add 30, so that becomes positive 16 equals 4v. And then we divide the 4 over to get v by itself. That gives me 4, and because it's a positive, that means my velocity is to the right at 4 meters per second. Momentum of the 3 kilogram after, so now we're looking at the after. Still mass times velocity, but now I have a new velocity of negative 10, so the momentum of the 3 kilogram after is negative 30. Mass times new velocity of 4 gives me momentum of 16, positive because it is to the right. And then total momentum after is the two of these together, and that gives me P total is negative 14. And then you'll notice the total momentum after and the total momentum before are the same. That's good because total momentum has to stay the same because it is conserved. The 3 kilogram objects change in momentum. So let's think about, the 3 kilograms started with 18, and then it went to 3 kilogram after was negative 30. So the change is just final minus initial, and that gives me negative 48. You also could do the side of the equation that means change in momentum, m delta v. The mass was 3 kilograms. Change in velocity is final minus initial for velocity. It ends at negative 10 and it starts at 6, so negative 10 minus 6 would be 3 times negative 16, which is the same answer, negative 48. So it doesn't matter which way you get it, you get the change is negative 48. Change of momentum for the 4 kilogram. So it started with negative 32 and it ended with 16. So final minus initial. When you subtract a negative, that becomes positive. So I get positive 48 is the change of momentum. Or I could do m delta v. It has a mass of 4. Final velocity was 4 minus the initial velocity was negative 8. So that becomes 4 times 12, which again is positive 48. And then you'll notice that this guy's change in momentum is the same as the second object's change in momentum. It's just this one's negative and this one is positive, meaning that this one is losing 48, whereas this one is gaining 48 units of momentum. The impulse. So impulse is the exact same thing as change in momentum. So if I want the impulse of the 3 kilogram, then I want the change in momentum of the 3 kilogram, which was negative 48. And then if I want the impulse of the 4 kilogram, that's just the change in momentum of the 4 kilogram, which is positive 48. And then we can also think through, so if the impulse is F delta t, well, we don't have force or time, so we couldn't find it this way, but again, it's the same as change in momentum, m delta v, so we can just use these. What a negative for an impulse means is, well, your time can't be negative, that just means you have a negative force. So that feels a force directed in the negative direction, which would be to the left. So if you think about the 3 kilogram did feel a force to the left when this guy hit it, and the 4 kilogram did feel a force in the positive direction to the right when this guy hit it. And then the change in velocity, well, that's just final minus initial for velocity. The 3 kilogram ended at negative 10, and it started at 6. That's a change of velocity of negative 16. 4 kilogram, still the v final minus the initial, ended at 4 meters per second, and it started at negative 8. So that becomes change of velocity is 12. So you'll notice that they change the same amount of momentum, one gains, one loses. They do not have the same change in velocity. In fact, the 3 kilogram has a greater change in velocity than the 4 kilogram because it has a lighter mass. Object with a mass of 3 kilograms begins with a speed of 2 and increases to 5 in 10 seconds. So m, vi, vf, and t. And we are looking for the impulse. Impulse is f delta t. Don't have f, so what we can do instead is use m delta v. And we have the mass is 3. Change of velocity is just final minus initial, so that's 5 minus 2. 5 minus 2 is 3, so that just gives me 9. And now I'm actually asking for what that force is, so we're going to plug into the entire side of the equation, because I don't want just the impulse, just one side. I want to find the missing force. So F times time was 10 equals the mass 5 minus 2. We already decided this side of the equation is 9, so F times 10 equals 9. To get F by itself, we're going to divide the 10 over, so that gives me a force of 0.9. The speed of a bullet leaving the muzzle will be the same as the speed of the recoiling gun. So let's think about it. If I have a gun and a bullet, at first they're at rest, so my total momentum is equal to 0, and then it's shut off, the bullet goes off, and the gun goes the other way. Now normally the bullet would be going much, much faster because the bullet has less mass. So if I'm saying that the gun goes off at the same speed, the only case where the gun and the bullet would go off at the same speed is if they have the same mass, so D. Momentum is always conserved, so A is always true. That doesn't mean they have to go at the same speed, it means they have to go at the same momentum. The only reason it would go at the same speed is if they were equal masses. Because if not, the lighter one goes faster and the heavier one goes slower. We've got 2 equal mass carts going towards each other. One rolls right at 2 and the other one rolls left at 1. And then after they collide, they couple together, which means they stick together, they attach, and we're trying to find the speed that they go off with. Now I don't know what the mass is, so what you can do is you can just call it m. And it says they're equal mass, so these are all the same m. So then it's m times 2 plus m times negative 1 equals mv plus mv. 2m plus minus n just gives me m, because 2x minus x gives me just x. And then mv plus mv is 2mv. So then if you're trying to find that missing velocity, divide the 2m over. M's cancel out and you're left with 1/2, which is 0.5. Now some of you do not like using m, so let's make up a mass. Let's say you use 5. As long as you keep it the same for both because they're equal, this will work out. So I have 5 times 2 plus 5 times negative 1 equals 5e plus 5e. That's 10 minus 5 equals 10v. That's 5 equals 10v. Divide by 10, and I get 1/2 or 0.5 again. Firing of a bullet causes the rifle to recoil backwards. The speed of the rifle is much smaller, so the rifle goes back slower than the bullet is because the rifle has a much larger mass. They have the same momentum, but the lighter one, the less mass, goes much faster, and the heavier one, the more mass, goes much slower. Cars are equipped with padded dashboards, so the padded makes it softer, which means instead of stopping immediately when it hits something hard, it stops over more time because it's softer. So we are increasing the time, and by increasing the time, that therefore decreases the force because you still have the same change in momentum, the same impulse, that would be constant. Because, right, you're coming in at some velocity and stopping. And then the F delta T part, well, if I increase this and this stays the same, then this must decrease to balance out to keep the same change in momentum. That's an arrow down, by the way. A wad of chewing gum is moving with a momentum of 1 collides a box initially at rest, which obviously is momentum of 0. And then the gum and the box stick together and they go off with some velocity. And I want to know what their combined momentum is. So the two of those momentums together, let's call that P total. Well, the P total beforehand was 1 and 0, which is 1 So the P total after has to be 1 unit. That momentum it can't be less because that momentum has to go somewhere, and it can't be more because then where did that momentum come from? Now, each individually has less than 1 unit, but together, combined, they have 1 unit of momentum. A -5 Newton force, mass, and from VI to VF, what is the impulse? So impulse is F delta T, can't use that, so we'll use M delta V, the other side, which is equal. 3, and then change in velocity is final minus initial, so that's 3 times -6, which is -18. And then B is asking how long the force is applied, so we're looking for the time. We just plug in force times the delta T is what I'm looking for, equals the M change in velocity. And then we already just said this side was -18, 3 times 3 minus -9. So that's -18, -5 delta T. To get delta T by itself, we'll divide the -5 over, and that is going to give me a time, get that one in my head, of 3.6 seconds. Cart 1 is 0.5 kilograms pulled with a 1 Newton force for 1 second, and cart 2 is a new mass, so I'll call this M2, and new force and new time. And I want to know which one has a greater impulse. Well, impulse is defined as F delta T, so for cart 1, that would be force 1 times force 2, times time 1, so 1 times 1 gives me 1. And then for cart 2, my force is 2 and my time is 0.5. Again, we're doing force times time, and that gives me 1. So it's actually the same because they both have an impulse of 1. So they have the same impulse right here. This one does have a greater force, but it's for less time. And this one has a smaller force, but it's for more time, so that balances out. Greater change in momentum. Well, change in momentum is the exact same as the impulse. So if they both have an impulse of 1, then they both have an impulse, they both have a change in momentum of 1. So again, it is the same because they both have change in momentum of 1. And the reason is that change in momentum is equal to the impulse. Now, change of velocity for each cart is actually not going to be the same because they have different masses. So for cart 1, we're going to plug in 1 times 1 equals mass of 0.5 delta V. Divide the 0.5 over, and that's going to give me a change of velocity. 1 over 0.5 is 2. And then so that's for cart 1. For cart 2, F delta T equals F delta V. My force is 2 newtons for 0.5 seconds, and my mass is 0.25 change of velocity. So this side has the same impulse, right? We got 1 on both sides, but I need to divide the mass over to get change in velocity. And when you divide 1 over 0.25, you actually get 4 is your change in velocity. So what's happening here is they both feel the same impulse, but this one is going to end up getting faster because it has less mass than the other one. Graph, we were trying to find the change in momentum. Change of momentum is M delta V. We were given the mass of 85, and we need to find the change of velocity from 0 to 2 seconds. So 0 to 2 seconds is this right here. And we were given a graph of the velocity. So the final velocity was 8, and the beginning velocity was 0, so it changed by final minus initial, 8 minus 0. So that's just 85 times 8, which is 680, I think. Yes, 680. So that would be the change in momentum from 0 to 2 seconds. And then it also asked about from 2 to 8. So what you'll notice here is that the velocity is not changing. It stays 8, 8, 8, 8, 8. So then your momentum would not be changing because it would be 80, right? Your momentum at the beginning would be 85 times the 8 meters per second. And that's what it is at the end. Or you can plug into your M delta V. Mass is still 85. The final velocity at the end of the 2 to 8 seconds is 8, and the initial velocity was 8, so 85 times 0 equals 0. So there is no change in momentum in that second section. Two blocks on a frictionless surface have the same mass m. Block 2 initially is at rest, and this one comes with the speed of 4v, and it collides inelastically, meaning they stick together. So you can think about when this comes in and it sticks with the second mass, we are now doubling its mass, so more mass means it's going to go slower, so we can cross off D and E, because we know that it goes slower. Now if we think about it, it comes in with 4v when it only has 1 m. When I go to 2 m's, that's twice the mass, so it should be half the velocity, 2v. Or you can actually just plug in, so you have 0 at the beginning, the second mass has a velocity of 4v. At the end, you still have mass m, and I'm not going to call it v because I already have a v in my equation, that's a different v, so I'm just going to call it question mark. This goes away, so 4mv equals, well, m times question mark plus m times question mark is 2m question mark. If you want to call it an x, that's fine, it doesn't matter. And to get the question mark by itself, divide the 2m over, m's cancel, and then it's 4 over 2, which is then 2v, which is what we guessed. An object with mass will have momentum, not always true, it has to have velocity. Momentum is conserved quantity. The momentum of an object is never changed. Not true. You can change momentum if it's slowing down or speeding up. The total momentum can never change, which is different than what it says. Two objects of different mass at different speeds. The more massive will always have the greatest momentum. Not true, because I could have a mass of 5 and a mass of 10. If this is going at 1 meters per second, or wait, the more massive. If this is going at 1 meters per second and this is going at 100, this would be more massive, but this would definitely have more momentum. So, not always true. A force of 100 newtons for 1 second would provide an equivalent impulse for a force of 5 times 2 seconds. Well, let's think about impulse is F delta T, so 100 times 1 is just 1, or 0.1 is just 10. And then 5 times 2 is again 10. So I might have a much bigger force here, but it's for a much smaller time. And here, a smaller force, but for a longer time, can provide the same impulse. So that is true. The net impulse is equal to its momentum change. Yes, impulse does equal to change in momentum. Kilogram meters per second is equivalent to Newton seconds. Yes, that is true, because if you look at your equation, F delta T equals M delta V. Newton is measured, or sorry, force is measured in newtons, time measured in seconds. Mass measured in kilograms, velocity in meters per second, so those two have to be equivalent to each other, which is why we see it both ways. While individual objects may change their velocity, the overall or total velocity is conserved. Definitely not true. Velocity is not conserved. Momentum is. Total momentum is always conserved between two objects in a closed system involved in a collision. Yep, that is definitely true. And when a moving object collides with a stationary object, the stationary encounters the greater momentum change. No, that is not true. They encounter the same momentum change. And total momentum is conserved in an elastic, but not in an inelastic. No, not true. Total momentum is always conserved. A 0.5 kilogram tennis ball launched from a 1.5 kilogram cannon. The cannon recoils with the speed of 2, so that's going backwards at -2. And I want to know what this velocity is. Well, this one is lighter, so it must be going faster. And the key here is they both were at rest before the tennis ball was launched. So we have 0 equals 1.5 times -2 plus 0.5v. So 0, this is just -3 plus 0.5v. Add the 3 over 0.5v, divide the 0.5 over, that gives me a velocity of 6. And we said that it was going to be faster, so this is faster than -2, so that's good. We've got a massive basketball, hits with a speed of 18, rebounds, meaning it's coming in at 18 and goes the opposite way, so we have to put a negative sign to show that that's a different direction. That would be my final velocity and my velocity after. Contact time would be 0.1 seconds, and we want to know the force on the wall. So this is our F delta T equals M delta V equation. We know because it's talking about force. And we're looking for force. Time was 0.1, mass is 0.53. Velocity is V final minus V initial. That's how you find change of anything. And so -13.5 minus 18. Final minus initial. On this side of the equation, let's flip it over. So on the right side, we would end up with negative 16.695. This side is still force times 0.1. To get F by itself, we divide 0.1 over. That crosses off, and that gives me a force of negative 166.95 newtons. And the negative just means like the force would be directed in the negative direction, or like to the left in this case. 2 kilogram box attached to by a spring to a 5 kilogram box. They're initially at rest. So this is my before picture. The string is cut and the spring applies an impulse to both boxes, setting them in motion. The 2 is propelled backwards at a speed of 2.4. So I'm going to put a negative sign because that's like my left or backwards in the negative direction. And we want to know the velocity of the 5 kilogram when they go apart. So key thing here is at first it was at rest, so the both momentum is 0. And then after, because your total momentum has to stay the same, it has to stay 0, these two are going to cancel out momentum, but not velocity. The 2 kilograms should be going faster, and the 5 kilograms should be going slower because this has more mass and this has less mass. So 2 times negative 2.4 plus 5, looking for the velocity. This is just 4.8. 5v, add the 4.8 over, and that gives me 5v. Divide the 5 to get v by itself, that gives me a velocity of 0.96. And we knew that it was going to be slower than the 2.4, so that's a good check. We've got a 0.5 kilogram cart moving at 36.4, and there's initially a second cart that was at rest. The 2 carts hit and they move off together with a speed of 21.8 after, and we want to find that missing mass. So now we're just plugging in 0.5 times 36.4 plus mass, but it was at rest, so times 0 goes away, equals 0.5 times its new velocity of 21.8 plus mass times its same velocity because they are stuck together. And now this side is 7.3. No, sorry, that is 18.2. This becomes 10.9 plus m times 21.8 is just 21.8 m. Now I cannot combine these because they are not like terms, so I have to subtract this over first. So subtracting the 10.9 over, that's what gives me the 7.3 is 21.8 m. And now still trying to get m by itself, so we need to cross off the 21.8, and we do that by dividing it over. And that gives me a mass of 0.33 kilograms. We've got a 9,230 kilogram truck colliding head on with a 1,250 kilogram parked car, so this one's not moving. They entangle together and they slide off at 3 meters per second. So that is together at the end they have a velocity of 3, and we're looking for the truck's initial velocity, so it's before velocity, so that's my unknown. So 9230V plus 1250, but it's at rest, so that goes away, equals 9230 times the velocity of 3 plus the second mass, 1250, with the same velocity of 3 because they are stuck together. So on the left, we get 9230V. This number plus this number, you can combine because they're just like terms, so just put it in your calculator. You get 31,440. And now trying to get v by itself, so we need to cross off the 9230 right here. And when we divide, we get a velocity of 3.4. And it makes sense that this was bigger than 3 because when it was coming in, it was going faster. Because as soon as it hits the second car, it picks up more mass, so this one should be slower, which 3 is slower than 3.4. In a physics lab, 2 carts collide elastically. Cart A has a mass of 1.5 and is moving east at 36.5. Cart B has a mass of 0.5, it's moving west. So as soon as it's going the opposite direction, or left or west, we need to put a negative sign there. And we want to know the post-collision velocity of cart B. So we're looking for this velocity if cart A moves 10 west. Again, west should be a negative sign. Now we just plug in m1v1 plus m2v2, etc. plus 0.5v. Now this is just numbers, so we can put all of that into our calculator. We get 33.35. 10 or 1.5 times negative 10 is negative 15. and 0.5v. Now I cannot just put all of this into my calculator because there's a v right here. There's an unknown or a variable, so they are not like terms. So in order to start getting v by itself, we need to move the 15 over. It's being subtracted, so we are going to add the 15 over. That gives me 48.35 is 0.5v. And to get v by itself, we'll divide the 0.5 over, and that gives me a velocity of 96.7. Two carts initially at rest, so that means if both of them are initially at rest, they have a total momentum of 0 beforehand. And they are being pushed apart. I'm going to make this negative because it's going to the left, and then I'm looking for this guy's velocity. And I don't know the actual mass, but what I know is that this one has 3 times the mass, and then this one does, so I'm going to call it m and 3m. Now, just by process of elimination, we know that they were initially at rest, so their total momentum is 0, so they have to have the same momentum, so they can't go at the same velocity if they have different masses. In fact, this one is less mass, so this one is going to go faster, and this one is going to go slower, so we can cross off anything that's not slower. So we can cross off 0.33 because that's the same speed, cross off 0.99 because that's a different, that's getting faster. And then we can also cross off 0 because it can't be at rest because they have to cancel out momentum, so all that's left is b, 0.11. Now what you could have done is you could have plugged in m times negative 0.33 plus 3mv, where v is your unknown. This would just be negative 0.33m plus 3mv equals 0. We could move this over. It'd be 0.33m is 3mv. Because both sides we have an m that can cross off, and to get v by itself, you divide the 3 over. 0.33 over 3 is 0.11. Hold on, guys. Gotta take a break. Okay. 2 blocks have a spring between them that is compressed after the string is released. Block A moves to the left with a speed of 5. I'm going to make that negative because it's to the left. This one moves with a speed of 3. What is its missing mass? So mass is my unknown here. They both were at rest at first, and then they were released. So total momentum will be 0 beforehand. So now we can plug in 4 times negative 5 plus mass times 3. That's just negative 20 plus 3m equals 0. Add the 20 over, so 20 equals 3m. And then we're going to divide the 3 to get m by itself, and that gives me a mass of 6.67 kilograms. And we knew that this one had to be a bigger mass because it was going slower. So the fact that it went slower than this guy means this one was a bigger mass. And 6.67 is bigger than the mass of 4. We've got a bullet going from a rifle. They were initially at rest, which means the total momentum is 0 before and after, because total momentum stays the same. The bullet leaves with a momentum of 20. So careful there, because a lot of people read that as velocity, but it tells me the momentum of the bullet is 20, and it's asking what is the momentum of the rifle. Now the rifle does go slower, and this one does go faster, but I'm not asking about velocity, I'm asking about momentum. If this has a momentum of 20 and the total momentum is 0, this one has to have a momentum of negative 20, so that these add to 0. So answer is just negative 20. It's the same momentum but opposite because they cancel out to 0. 2 pucks are attached on a stretch spring. They're held initially at rest and then they're released, and puck 3 has 3 times the mass of puck 2. What do you know about their momentums? Well, P total was 0 before, and it has to be 0 after, so it's before and after. So if you have a total momentum of 0 and these two are moving apart from each other like this, then that means that they have to have the exact same momentum so that they can cancel to exactly 0. So they have to have the same momentum, and I'm going to put but opposite directions to cancel to P total equals 0. Now some of you are sitting and looking at number 1, you're like, but it has more mass. How come it doesn't have more momentum? More mass only means more momentum if they're the same velocity, which they are definitely not, which brings us to part B, the velocities. So puck 2 is definitely going to go faster because it has less mass, and puck 1 is going to go slower because it has more mass. So I can't say, like, oh, this has more mass, so it has more momentum. It does have more mass, but it has less speed, so that balances out where they have the same momentum. Which one has more momentum? So we're just going to multiply mass times velocity. This gives me 75. Mass times velocity gives me 50. Mass times this velocity gives me 100. Mass times this velocity gives me 75. So the one with the most momentum is C. 100 is bigger than 75 and 50. What happens to astronaut A's speed and B's after the collision? Well, first he's at rest and then they're moving. So B definitely got faster because he wasn't moving at first and now he is. Now A was coming in with some velocity, and then when he joins up with astronaut B, he gains more mass, so he has to get slower. He is giving away some of his momentum to astronaut B, so he slows down and B gets faster. So astronaut A gets slower and B gets faster. Same force for the same amount of time. This is talking about my FTMV equation. If this is the same and this is the same, then they have to have the same impulse, because impulse is F times time. If F is the same for both and time is the same for both, then the product of them has to be the same. So they have the same impulse, and impulse is the exact same thing as change in momentum. So whatever this answer is, this one has to match, so then they would both have the same change in momentum. Now they would not have the same change in velocity because they have different masses. So let's think, I want more change in velocity. I want to know which one goes off at a faster speed after that same force for the same amount of time. I want them to still be equal on this side, so if this is more, then that means the mass must be less, because this going up and this going down balances out to equal on the other side. You also can think about it's harder to get this one going faster because it weighs more. So if they have the same force for the same amount of time, this one would end up going slower and this one faster. So greater change in velocity was B because it has less mass. Force of 20 newtons on a cart for 10 seconds. How long would you need this new force to produce the same change in momentum? Let's think change in momentum is m delta v. We don't have that, but it's also F delta t, so let's use F delta t. 20 times 10 would give me a change in momentum of 200. I want to keep the same change in momentum, but now I only have a 50 Newton force. So I have I have a bigger force now. So if I have a bigger force, it would need to less time, so it can cross off A, that's the only one it can cross off. So I want still 200. But now I have 50, so what time would be needed? Well, we just divide the 50 over, and that's going to give me 4 seconds? Yeah, 4 seconds. Study hard, guys. Good luck.